So we're going to talk about refraction and Snell's law today. Okay? Refraction and Snell's law. So Snell, yeah, Snell. So there's Willibird Snellius, and he came Snellius. Yeah, there might be two L's. Uh, and kind of an Enlightenment era guy, and he is essentially credited with whether he actually came up with it himself, but the geometrical relationship that is found during refraction. Okay, and I'm going to write his law. I'm going to write his law first, and then we'll talk about what it means. So his law essentially is n1 sine theta 1 equals n2 sine theta 2. I think it's actually called Snellius-Descartes law, but we just can refer to it as Snell's law. So Snell's law is n1 sine theta 1 equals n2 sine theta 2. And to start off here, let's draw a little picture and figure out what we mean by this and figure out what we mean when we say refraction. So before we draw a picture, refraction is the change in direction, or often called the bending, the change in direction or bending of wave rays as the rays pass into different materials. Okay? Or different media, I guess, is probably a better way to put it. So the example that we did live was we looked at water waves refracting. And so to draw that, let's just let's draw some wave fronts here. Okay. So if we have some incident waves that are coming towards a surface, and what we did was we put an area where there was shallower water, right? If you remember doing that, we just represent that as a slightly different area here. Bigger. Put it at an angle, and we'll change it to that color. Okay. So the waves are striking the surface here, okay, of a shallower area. That's what this is meant to represent. So this is deep. You want deep water. And this is shallow water. And we notice that the waves did not continue on in the same direction. So if I draw a normal line in here, like that, remember the normal is to the surface of the interface between the media. Okay. What we're going to find is that the water actually like bends, in this case, towards the normal. So you end up with like a smaller wave like that, and you end up with this. Let's just draw these in. So the wave path will be altered as you travel into the new media, as will the wavelength. Okay, the wavelength will change as well. Now what's going on here is this. Let's just change the color of the normal because it's a little bit too similar to what we've drawn there. Okay, perfect. So what's going on there is this. As the waves enter an area of shallower water, they slow down. Okay, the frequency stays the same as we learned between different media. So the frequency stays the same, but if these are traveling more slowly, you're going to get a shortening of the wavelengths. Okay, the wavelengths will shorten because the frequency needs to be maintained at the same level. So there's no change in frequency. Frequency 1 equals frequency 2. And that's sort of an important thing, so let's just write that down. The frequency of the source equals the frequency of the refracted waves. So these frequency-wise equals these frequency-wise. In this case, the way we have it here, velocity 1, the input velocity, is greater than velocity 2. Okay? We're also going to draw in an angle as measured from the normal, called theta 1, and there's going to be a theta 2, which is an angle also measured from the normal, but after refraction. Theta 1 is larger than theta 2. Okay? So what we can say here, okay, so here's sort of what we were talking about. If these represent incident waves coming in here, when they strike a shallower area, and this is meant to represent looking down on top of water waves, and this is a shallower area where someone's put like a triangular piece of glass, you will get a bending of the wave as it strikes that surface. So here comes some incident wave fronts here, and here's their refracted direction. Okay, so the actual wave fronts themselves are bending as we go. All right, and hopefully you can see there that they're actually, what's going on is their wavelengths are shortening. I haven't drawn these perfectly perpendicular or parallel to one another, but they're pretty close. Now let's draw in our wave rays. Okay, so you have wave rays here coming in, right? And then you have wave rays here for your new waves. All right? Now your normal in this scenario would be the interface between the two pieces of glass and the water. So there. Okay? Like that. And if you go right here, pull this up, we should be able to see that if you measure from the wave ray to the normal, here's theta 1, if we're looking at this particular one, and here is theta 2. So you'll see that as water gets into a shallower area, the theta 2 ends up being a smaller value than the theta 1. In other words, the wave bends towards the normal. Over here, it's in a faster medium. Over here, it's in a slower medium. Okay? And that is essentially what we're kind of talking about here. All right? Are you with me so far? So what was sort of noticed about this scenario here? Okay? And I'll just, you know what, I'll draw like one simple one here so you can maybe follow along a bit better. But if this represents a slow area, and this represents a fast area, right? We could say that there is a velocity here, and we'll call it v1. And we could say that there's a velocity 2, which we'll call v2. Actually, I'm going to switch that around. Hang on a sec. Sorry, that's what we want to say. We want to go from a fast to a slow area. Yikes. Okay, so we're going to have a velocity 1 here and a velocity 2 here. And we're going to have incident wave rays striking like this. Now be aware, this represents the wave ray, right? Not the wave front, but the wave ray. We're going to put in a normal here. Like that. And we'll just move it to the spot that we need. There. And apparently I can't generate a new one for some reason. Come on, thing. Okay, so this is what we're talking about. A wave ray coming in from a fast medium and going to a slow medium. And when waves slow down, we get a refraction towards the normal. Okay? So let's just mark the normal here. And we draw the normal as being just a line perpendicular to the interface between the two mediums. So this is our normal. Now the other thing to remember is that there's usually some reflection here as well, but we're just going to leave that out for the purposes of keeping this as simple as possible. Okay? Now what's happening here is wave fronts are coming in and their wavelengths are shortening. So the way that I like to make this, or try to make this make sense to people is kind of this. What will happen is the wave front over here, so the part of the wave front that's like, say over here somewhere, like this part here, is actually going to strike the surface before the rest of the wavefront. So in other words, part of the wavefront will slow down before the other part of the wavefront slows down. Okay? This causes like a torquing action, if you want, overall on the wave. And you'll get your new wavefronts kind of that end up being like this. Shorter wavelength, right? But traveling in a slightly different direction. So to help you think of this, imagine that this represents the sidewalk and this represents your grass lawn. And let's say that you have two wheels on an axle coming in and striking the interface between these two different surfaces, right? So if we have a wheel and axle coming in here and interfacing there, you can imagine that this wheel here will hit first, right? This wheel will hit first and slow down, and what that'll do is it'll swing this wheel over because it's traveling faster, and you'll get a bend towards the normal, right? The normal would be here. So you get a change in direction such that it goes towards the normal. Does that make sense? As the wave slows down, it bends towards the normal, okay? So there's a couple of ratios here, and they work like this. V1 over V2 is equal to the ratio between wavelength 1 and wavelength 2, okay? In other words, the ratio between speeds works out to be the same as the ratio between wavelengths. So for example, let's say V1 equals 10 meters per second and V2 equals 5 meters per second. Well, the ratio of 10 to 5 is like a 2-to-1 ratio, right? So then if wavelength 1 was equal to 1 meter, what do you expect wavelength 2 to be equal to? Half a meter, okay? So that's a nice sort of whole, way of dealing with problems with this sort of stuff is through this simple kind of relationship. Now, you're not going to exactly know what I'm talking about just yet, but this is also true, and this is for dealing with light waves, and we'll talk about this in just kind of this scenario. N2 over N1 works out to be equal to sine theta 1 over sine theta 2. This is actually Snell's law just written slightly differently. But this is also true, okay? And so we're going to make a bunch of things equivalent to one another. And then we can write out a big, long equivalency. So if N2 equals N1, and that also equals sine theta 1 over sine theta 2, then we should also be able to say wavelength 1 over wavelength 2. We should also be able to say V1 over V2. So this is like the sort of large, all-encompassing refraction ratio here, where theta 1 is always the incident wave ray as measured from the normal. So it's the angle from the normal for the incident wave ray. An incident is always the incoming, right? And then theta 2 is the refracted wave here after refraction has happened. Okay, so incident is where it's coming from, refracted is where it's going. Okay, so this is kind of an overall thing. It's not written this way on your formula sheet, but that's kind of the overall deal with this. Okay, so let's try a problem here. Let's go back to V1 and V2, and then let's talk about angle 1 and angle 2. So let's write one more water-related problem. Let's go back to our initial. Okay, let's say, so V1 was 10 meters per second. V2 was 5 meters per second. Let's say that theta 1, the incident angle, was 35 degrees. Well, what would the refracted angle be in that scenario? So to draw a quick little picture here, it would be, again, this kind of scenario. Here we have this. We've got our incident wave like that. We've got our normal here. There we go. And here like that. Let's just make sure that we know that this is incident wave. It's coming like that. Our refracted wave down here like this. Okay, this is 10 meters per second. Whoops. This is 10 meters per second here. This is 5 meters per second here. Here's theta 1, and here's theta 2. Now, the law says that V1 to V2 should be the same as the ratio between sine theta 1 and sine theta 2. It's not theta 1 to theta 2 directly, it's sine theta 1 to sine theta 2. So we need to solve, we need to isolate for sine theta 2, okay? So to isolate for sine theta 2, you got to do some algebra. So your first thing probably is to get it off the bottom, okay? And then work back the other way. So if we do that, we should get this multiplied by sine theta 1. Quick algebra review as we go here. Oops, sorry. Something looked wrong there. Okay, so then we got to multiply by V2 to get it over there, so we end up with this. And then we got to divide off V1. And the last thing is we have to do the inverse sign because we want the angle. We don't want the sine of it, we want the angle. So theta 2 is the inverse sine of all of this stuff. Okay, so there's your little algebra review, rearranging a formula. And what we'll get from here is we'll get this. So sine of theta 1, what did we say theta 1 was, angle-wise? 40 degrees, was it? 35? Okay. And V2 was 5 meters per second. And V1 was 10 meters per second. And now we just got to solve. So get out your calculators and give it a try. So if you do your calculations correctly, and I highly suggest you try it out, you will find that this works out to be 17 degrees. This is pretty much what you would expect. The angle has to be smaller. This is slowed down. The refracted angle is expected to be a smaller angle, so this should make sense. Theta 2 is 17 degrees. So this is a version of Snell's law, okay? There's a couple of other things to deal with here. One other thing I want you to notice is, well, what happens if we go from slower medium to faster medium? What if we switch this up and go in reverse? So let's draw that scenario. We'll draw an interface between a slow medium and a fast medium. And we'll draw an arrow of a wave rate coming in contact with a surface. And we'll put in a normal. Like this. We shouldn't make it the same color, actually. Let's make it a different color. And we'll put it in the right spot. So here's your normal. Now what this could be is coming from shallow water into deep water, right? From an area like where the water is maybe 2 centimeters deep to an area where it's like 8 or 10 centimeters deep, okay? And what you would expect is, what do you think is going to happen to theta if you go in the opposite direction? I think you'll think hopefully you think this, that you're actually going to bend away from the normal now as you speed up, okay? Now the reason being is that this part of the wave over here, right? Remember we're showing wave rays here. So what this really represents, of course, is wave fronts like this. Well, these wave fronts are striking the surface before the rest of the wave, and they are speeding up. And not only that, what do you expect to happen to the wavelength as you go from a slow to a fast medium, understanding that the frequency has to remain the same? What do you think is going to happen? Yeah, the wavelength would end up increasing, right? Because they're traveling faster, wave fronts are hitting more often, unless you lengthen out the wavelength, right, in order to have the frequency remain the same. So this is theta 1 now, right, because it's the incident wave here. This is theta 2 now, right? So when, and this is V1, and V1 is slow now, and V2 is fast, okay? And the wavelength here is short, and the wavelength here is long, okay? So let's, keeping this in mind, try one more scenario. The ratios always hold true. It's just that now your incident is coming from a fast medium, or from a slow medium and going into a fast medium. So if we say theta 1 equals 25 degrees, okay, and we say that V1 equals 5 meters per second, and we say that V2 equals 20 meters per second, theta 2 equals question mark. Just before we go about solving this, I just want you to change this to 8 meters per second. 20 meters per second is too high, and something weird will happen, which we haven't got there yet. We'll exceed what's called the critical angle. We don't want to do that. So let's drop that down to 8 meters per second and solve it that way. So I'm just going to rearrange this, and then we'll jump back in with numbers. Okay, so if you rearrange your formula to solve for theta 2, you should end up with this equation. And theta 2 should come out to be, at the end of the day, about 43 degrees, okay? So as you go from slow to fast medium, right, you're going to increase your angle, okay? And I think that's good for today, at least for this topic.